Iron Man 2008, the Mark II suit leads Tony Stark to hover, accelerate across his working center, launch vertically, and complete a curved mid-air turn. These movements appear smooth and believable, but the question is whether such actions follow real physics. This video analyzes the clip from 1 minute 14 seconds to 1 minute 49 seconds using Newton's laws, kinematics, thrust, kinetic energy, and centripetal acceleration to determine whether these motions could realistically occur. At 1 minute 14 seconds, Iron Man performs a control hover. At 1 minute 17 seconds, he accelerates horizontally. Between 1 minute 21 and 1 minute 23 seconds, he rapidly rises vertically. At 1 minute 35 seconds, he executes a tight turning motion. From 1 minute 38 to 1 minute 49 seconds, he maintains fast horizontal movement. These segments provide usable measurements for displacement, acceleration, velocity, and turning radius calculations extracted through frame-by-frame video analysis. A realistic evaluation begins with Newton's second law, F equal ma. Hovering requires upward thrust equal to weight mg, producing zero net force. Therefore, any rise requires thrust greater than mg, creating positive acceleration. The upward acceleration visible in the clip allows calculation of the exact thrust Mark II suit must generate. Newton's third law explains the origin of thrust. The suit expels gas downward with large momentum, producing an equal and opposing upward reaction. Realistically, this would generate destructive downward pressure, shock waves, heat, and turbulence, none of which appear in the movie. Ignoring these consequences highlights a common difference between cinematic portrayal and real propulsion physics. Kinematics equations, including v equal 1 over 2 at squared and v equal u plus at, allow precise calculation of acceleration and velocity from measured distances and time. Because the movie never states numerical speeds, these equations translate observed motion into quantifiable physics. Centripetal acceleration, AC equal v squared over r, describes the inward force required for Iron Man's turn. High velocity and a small turning radius produce large g-forces, which place extreme stress on the human body. Kinetic energy, Ke equal 1 over 2 mb squared, reveals the energy Iron Man carries during high-speed flight. This energy level determines the danger posed by collisions and the difficulty of stabilizing such motion. Together, these principles create a scientific foundation for judging the scene's realism. Using vernier video analysis, I tracked Iron Man frame by frame. The movie runs at 24 frames per second, so each frame equals 0.042 seconds. I used Tony Stark's height, 1.85 meters, to set the scale, converting pixels to meters. My measurements showed Iron Man rising 14 meters in 2 seconds, traveling 80 meters in 1 second horizontally, and covering 60 meters in 1 second during his turn, with a turning radius of about 5 meters. These values provide a basis for the numerical calculations. For the vertical acceleration, using kinematics formula, A equal 2d over t squared is equal 28 over 4 equals 70 meters per second square. The mass of suit with Tony is equal to 374 kilograms. The weight results in 3,665 newtons. The required thrust is F equal m times g plus a, which is equal to 6,283 newtons. The horizontal kinetic energy is calculated by the velocity of 80 meters per second. The Ke is equal 1 over 2 mb squared, which results in 1.2 times 10 to the power of 6 joules. The centripetal acceleration used by the velocity of 60 meters per second and radius of 5 meters results in the acceleration of 51.2 meters per second squared, which is 5.2 g using the gravitational force as 9.8 meter per second squared. Because the Mark II suit requires 6,280 newtons of thrust over triple the 1,900 newtons produced by the strongest real jetpacks, carries about 1.2 million joules of kinetic energy equivalent to 1,100 car crash, and generates about 5g during its turn, a level at which untrained humans typically black out. Iron Man's movements are physically impossible in real life. Visually, scenes like this may inspire viewers to develop real-world assistive technologies. However, it can also mislead viewers, especially younger audiences, into believing that hovering suits, vertical launches, and high-speed exosuits are achievable, feeding misinformation about physics, safety limits, and human tolerance, and shaping unrealistic political expectations about military technology and government investment. Movements require thrust energy and g-forces exceed real physics, showing the clear gap between movie action and scientific reality.